Hello everyone, I am back today to be continuing on with our lectures on gases. We are on page 5 of the AP outline called Gases, and today we're going to take up the story of Amedeo Avogadro. And this is what has created such a nightmare in your lives for the last several weeks, because Avogadro's hypothesis was the birth of the idea of the mole. So what Avogadro said was that equal volumes of gases at the same temperature and pressure will contain equal number numbers of particles. Now what we need to remember here is that when we are measuring moles, what we're really measuring is the number of particles that are present in a sample. So this was our very first foray into the word of moles. So now we could have an Avogadro's law. We could say that moles over volume would be directly proportional. Meaning, I wrote that not the way I wanted to. I wanted to write it that way. As we increase the number of particles in a balloon, meaning I blow into it more and more and more, the volume is going to get bigger. Okay? So we could say VI over Ni equals Vf over Nf. Not that that actually comes up that often, but it is possible for us to say that. And what that does really is it allows us now to complete our discussion of all of the parameters that we've been talking about: pressure, volume, temperature, and moles. And we're going to use that to segue into the idea of ideal gases and what will become the ideal gas law. Okay? Now, before we can get into an equation to talk about the ideal gas law, we have to develop a few postulates, okay? A few statements that are going to describe an ideal gas. And these statements are not without flaw. In fact, we'll spend, a day talking about the flaws with the statements. But for now, the first statement: the particles are so small compared to the distances between them that their volume is negligible. There we go. Now, we had already started to mention a problem with that idea when we were dealing with the Charles law and the fact that the particles do take up a little bit of space. You can't have zero volume, okay? But in general, it's a pretty decent statement. 2, the particles are in constant motion. And some people like to say that that motion is linear. I typically don't put that in. Okay. the elastic collisions with the walls cause pressure. Okay, so we already started to talk about pressure a lot back in the first couple pages of the outline, okay, and how air, as an example, hitting onto the side, of you, pushing in, okay, that is air pressure, okay. You don't notice individual collisions, but you notice the net effect. Now, this statement is, in general, a really good statement. The collisions are pretty much elastic. They bounce off with pretty much the energy that they hit with, okay? The motion of the particles is constant. They're just always flying around. The only time they're not in motion is at absolute zero. We're not talking about that, okay? So, in general, number 2 is really quite a good statement, okay? Statement number 3, the particles do not exert any attractive or repulsive forces on each other. Okay? They don't interact. They don't attract. They don't repel. They just do not interact. And boy, there are going to be some big problems with that statement. Okay? Number 4. The Kelvin temperature of the gas is directly proportional to the kinetic energy of the particles that make up the gas. Now, this is a great statement. It really is. I've talked about the importance before of molecular motion when trying to define temperature. The more the particles move, the higher the temperature is going to be. Or perhaps if you're really looking for cause and effect, okay, raising the temperature causes the particles to move more. Okay? Kelvin temperature, that's what we're talking about because it's an absolute scale. We can't have any negative numbers here. Okay? All right, so these are our postulates about an ideal gas. Now, every textbook words them a little bit differently. And if I were to, do this again next period, I might even use some slightly different words in these statements, okay? But they are, as a general thing, always going to say the same, okay? All right, now, using what we know, we can just empirically write the ideal gas law. Now, we can derive it. It's probably derived in an appendix somewhere in the book, but it's like a 4-page derivation. But PV equals nRT. We know that pressure and volume are inversely proportional. We know that pressure and temperature are directly proportional, so they're on opposite sides. We know that volume and moles are directly proportional, so they're on opposite sides, okay? And we know we're going to need a constant in there, a proportionality constant, to make the algebra all work out for us. Now, not that we are really going to make a big deal about this next thing, but I wanted to do it right at least once. Officially, it is a lowercase p, a capital V, a lowercase n, a capital R, and a capital T. It turns out that volume and temperature are state functions and pressure and moles are not, and there'll be more about that in the next chapter. Now we can rearrange it different ways. My favorite is to say V equals N R T over P. And my reasoning for that is as simple as A, B, C. Volume and moles by Boyle's law. Volume and pressure by Boyle's law. Volume and temperature by Charles' law. And I think that's a nice way to remember the names of the laws. Okay, R is called the universal gas constant. I've listed it here in several different pressure units. You are most comfortable probably with the first one. We used that a lot last year. The second one is going to get used a lot this year also. Occasionally, I'll throw in a question like this just so that you can prove that you know how to use this value, but not going to come up in an AP exam situation. No point in memorizing this. These will be provided on the AP exam. They will be provided on the Chem Olympiad, and I will be providing them for you on all of my tests. Okay, that's the end of page number 5, and we'll be tuning back in for the next video for page number 6.